Assalamu alaikum, dear 11th science students. Last three classes I said about energy, kinetic energy, and I solved four numerical problem. Today I will discuss about the students work energy theorem, what is called work energy theorem, and I will discuss about potential energy. Along with I will discuss about principle of conservation of energy. So dear students, it's chapter 5. Work energy theorem. What is work energy theorem? Dear students, for understanding the work energy theorem, I have to say something. Just we think about or let a force be applied on an object of mass m, and the velocity of the object changes from b1 to b2 while the object travels distance s. Here the force is constant force. Okay, constant force means it doesn't change in magnitude and direction. Okay, now dear students, look at the picture. Okay, by applying force if the mass object gets acceleration a, displacement s at time t, final velocity v2. So from the equation motion we can write b2 square equal to b1 square plus 2as. Here b2 is final velocity, b1 is initial velocity, a is acceleration, s is displacement. From this we can write a equal to b2 square minus v1 square divided 2a. Dear students, we know from the definition of work, W equal to Fs. Here F is force, applied force, constant force, S is displacement, and we can put F equal to ma, Newton's second law. S equal to b2 square minus v1 square divided to a. We can write down half m b2 square bracket minus v1 square. From this we can write half m b2 square minus half m v1 square. So now we can say final kinetic energy minus initial kinetic energy. Dear students, so increase of kinetic energy of the object, we can say increase of kinetic energy. Finally we can say increase of kinetic energy of an object is equal to the work done by the applied force. In fact, it is the work energy theorem. Dear students, now I will deduce the work energy theorem from the variable force. Okay, now we will apply variable force. Let a variable force is acting on a particle, though the magnitude of the force is changing but its direction remains unchanged. In that case, the direction of the displacement will be along the direction of force. That the particle is moving along x direction. Now the amount of work done is moving the particle from 0 position to x position. Okay, dear students, we can write down work done W equal to integration 0 x f dx. Here f is applied force, variable force, dx is a tiny displacement. Now my dear students, we know from the Newton's second law of motion, F equal to ma. Here m is mass of the body, is the acceleration of the body, and F is the force, variable force. Again, we know from the calculus, acceleration equal to dv dt. Since this is calculus, that's why you have to say dv dt. Yeah, d dt is operator. Okay, we can say rate of change of velocity is called rate of change of velocity with respect to time is called velocity. We can write dv dx dv dx dt. Dx dx cross, that's why we can write this. Now dv dx dot v means dx dt. We know rate of change of displacement with respect to time is called velocity. Okay, so finally we get v dv dt. Now dear students, we can write work done w equal to integration 0x mv dv dx. We can write integration b naught v mv dv. We can write mv dv. We can write m. We can draw the m outside. Integration v naught v dv equal to m v square divided to v 0. From the integration formula, we can write this. Actually, here v is index 1. From the formula of integration, we can write down 1 plus 1, that is v square, and we get 2. It will be divided. That means 2 divided. The v 0 is the lower value and is the upper value of velocity. If you know the formula, you can understand why I have written this. So from this, we can write half mv square minus half mv naught square. We have just put the upper value and lower value of v, and minus here we have got from the formula. Okay, this is the actually work energy theorem. From this equation, we can say half mv naught square is the initial kinetic energy and half mv square is the final kinetic energy. We can conclude work done by variable force equal to change in the kinetic energy of the particle. Okay, this is our required conclusion. Now, dear students, if you are not interested to know details about deduction, you just remember this formula: w equal to half mv square minus half mv naught square. Okay, m is mass of the particle, v is the final velocity of the particle, and m naught is the initial velocity of the particle. If you remember this formula, you can solve a lot of numerical problem. Okay. Now, my dear students, it's a math. Look at this stem. The picture of a boy. The boy is throwing a marble by this catapult. The marble mass 0.0 kg. You have to enter when he throws this marble, it gets velocity 5 meters per second. You have to find out the change of energy. It's very easy. We know the formula half mv square minus half mv square. So we can write this half product 0.02 product 5 square minus half 0.0 product 0 square. And now you have to write e square, not 2. Okay. From this, you if you calculate by calculator, you will get 0.25 joule. Okay, with the energy change. Now, my dear students, what is potential energy? The ability of doing work gained by a body due to its change of normal position or configuration is called potential energy. Let me give some examples. When a body is raised to a certain height, work is done against the force of gravity. This work is stored in the body as potential energy. As the body falls to its initial position, it can do work. The principle is used in driving pile into the ground. Look at this figure. For the Padma bridge piling by potential energy, there are several pile, and this driving by potential energy. Okay. Now, my dear students, look at this animation of spring. In fact, when we raise a hammer, when we compress or expand in a spring, then there is a stored potential energy in the spring. So, if we place any particle or any body before the compressed spring, you will see it pushes, okay, the object. You can understand from this animation. And its potential energy half k x square. K is spring constant, x is the amount of expansion and compression. Okay, k is constant. Now, my dear students, when we raise hammer, that it gets potential energy. Okay, look at this animation. For the changing its position, it gets kinetic energy. Okay, you can understand actually the potential energy of hammer. The archery stores potential energy due to pulling. You can understand what is potential energy from this archery picture. At height, the object has potential energy. When anybody raises any substance at a height, then there is a stored potential energy, gravitational potential energy. You can see another picture. Here, a simple pendulum at A, the bob has potential energy. Okay. Now, my dear students, what is the classification of potential energy? There are 4 types of potential energy. One is gravitational potential energy. Second is elastic potential energy, electric potential energy, finally magnetic potential energy. But we will discuss here about only gravitational potential energy and elastic potential energy. What is gravitational potential energy? Dear students, suppose a body of mass F is raised to a height h from the ground. Some work has to be done against the gravitational force. This work becomes the potential energy stored in the body. Dear students, the force F necessary to raise the mass m vertically with an uniform velocity without any acceleration is equal to the gravitational force acting on the body, that is the weight of the body of mass m. So we can say gravitational potential energy equal to work done against the force of gravity. Look at this picture. Here, height m, the mass of the body m, and surface of the earth. Okay, so we can say we can say U equal to F is from the definition of work. Here F is force, F equal to mg, h is height. So finally we will get U equal to mg is. It's the record equation for gravitational energy. For doing mathematics, you have to remember this formula. If you know mass of any object and height of any body, plus you can find out the gravitational potential energy. Now, my dear students, the equation shows that potential energy depends on h, height. That means height, from where h is measured. That is, it depends on where h equal to 0 is taken. Therefore, potential energy is not an absolute property of any body or its position. Rather, it depends on the reference plane with respect to which it is measured. Suppose a book is lying on your reading table. You are holding a pen. You are holding a pen above the book. So what is the potential energy of the pen? Can you say me? The potential energy of the pen is different with respect to different planes. The potential energy with respect to the table will be greater than that with respect to book. It will be greater than that with respect to the floor of the room. So from the equation is observed that the gravitational potential energy of an object is proportional to the height. So dear student, you can say from this equation the gravitational potential of an object is proportional to the height from the reference plane. We have to remember this quotation. Okay. Now do a mathematics. Look at this picture. Here height is 2 meter and mass of the body 3 kg. Yeah. You have to find out the potential energy of the object. Okay. You know here what is the amount of object and what is the height. That's why if you apply the gravitational potential energy formula, you will find out potential energy. Now look at this this picture. How can you find out the potential energy of the bulb at position A? Here 2m and the mass of the body is 0.3 kg. You have to find out the potential energy of the bulb at A. Now, my dear students, potential energy of a spring. Okay, we have to deduct the formula of spring potential energy. For this, suppose a body of mass m is attached to one end of a spring. The other end of the spring is fixed to a rigid support. Look at the figure. The body can move over a frictionless smooth surface. You know that to stay the spring, work has to be done against the spring force. The work done against the spring force will remain as potential energy of the spring. That means the work done against the spring force will remain as potential energy of the spring. Now look at this figure. You can see a spring, its initial position x equal to 0, mass m, after extension X, F is applied force and Fs is a restoring force by the spring. So dear students, sorry, there is a disruption. Anyway, finally we can write E equal to half k x square. K is spring constant. Okay. In fact, this is our required formula for spring potential energy. For doing mathematics, we have to remember this formula. Okay. And from this formula, dear students, we can say potential energy stored in a spring is directly proportional to the square, the displacement of its free end. Okay. Let me give an example. When a spring fitted toy pulled backward, the spring being compressed stored potential energy. Now, when the toy is released, the spring is expanded and thus the potential energy is transformed into kinetic energy and moves the toy forward. It's very popular example. I guess you have understood. The toy potential energy convert to kinetic energy. Okay. Now, dear students, was the principle of conservation of energy. Was the principle of conservation of kinetic of energy. Okay, statement: energy can neither be created nor destroyed. Okay, it can only be converted from one form to another form. The total energy of the universe remains constant. Conversion of mechanical energy. You can understand from this animation what is conversion of energy. It's the mechanical energy. Okay, the car has potential energy at the top place. Okay, but when it gets a velocity or motion, then the potential energy converts into kinetic energy. Ocean thermal energy is also another type of conversion. Conversion of light energy. From this picture you can understand the conversion of light energy. From the light energy we get electrical energy from the solar cell, and by the light energy we can use a calculator, and we also convert light energy, electrical energy into a camera. Okay. Now, my dear students, now we will prove in case of a body falling along a smooth inclined plane. Okay. Let a body of mass m is sliding down a smooth inclined plane of inclination theta with the horizontal A of A. Look at this figure, then you can understand. Okay, A of A. Vertical height from A of E is h. Okay, vertical height h. At B, the kinetic energy of the body is 0. The kinetic energy is 0 at body at point B. So the potential energy at B, what will be the potential energy at B? Can anybody say what is the potential energy at B? the potential energy mgh. Here m is mass of the body, h is the height. Okay, the total energy, what will be total energy at B? The total energy, potential energy plus kinetic energy, potential energy 0, kinetic energy 0, potential energy mgh. Okay, total energy mgh. Now suppose the body slides along the inclined plane at C after traveling a distance x. The velocity as C is v. Okay, the velocity as C is v. Let CD is parallel to AFE and CF equal to y. For understanding, you have to look at the figure again. Okay, according to description, the force acting on the body along the inclined plane distance F equal to mg cos 90 minus theta mg sin theta. Here along the inclined plane, the force will be mg sin theta, and force comes from the weight of the body. Okay, now here acceleration A equal to, we can write acceleration equal to g sin theta, and displacement is equal to x. Okay, is equal to x, displacement this and acceleration this. The we can write potential energy at C mg cf. For understanding this, look at the figure again. CF means BE minus BD. B means H, BD means x sin theta. Now, dear students, kinetic energy at C. At C, what will be the kinetic energy? What will be the kinetic energy? We know kinetic energy means half mv square. Okay, half m into 2gx sin theta. B means b naught square equal to plus 2as. Okay, b square equal to b naught square plus 2as. Here b naught 0. Okay, that means finally we get mgx sin theta. It is kinetic energy. So total energy at C, total energy at C, potential energy plus kinetic energy. Potential energy mg bracket h minus x sin theta plus mgx sin theta. We can find, look at this, we can write this, and from this we get mgh. Okay, so total energy at B equal to total energy at C. So it is proved that for a body falling freely down the inclined plane, the total energy remains constant. Now, my dear students, in the this is case B. In the case of oscillating simple pendulum, in the case of oscillating simple pendulum, I know so far that you know what is simple pendulum. Let the effective length of the simple pendulum L equal to OA, the mass of the bob be m, the maximum displacement be B or D, and minimum displacement. Look at this figure, then you can understand what I have said. You have to understand the figure. Without understanding figure, you can't reach my point. Okay. Now, my dear students, minimum displacement be A. Look at the figure. When pendulum reaches point B or D, momentarily it remains stationary there and starts moving towards A. As it approaches A, its velocity increases and becomes maximum at A. So the total energy at A or B is potential energy, and total energy at A is kinetic energy. As the pendulum moves from A to B or A to D, its kinetic energy starts decreasing while potential energy starts increasing. On the other hand, when the pendulum starts moving from D or B, its potential energy starts decreasing. My dear students, and kinetic energy starts increasing. Let us consider that pendulum at an instant reaches from OB to OC, and the velocity at C is V. Now, if BP and CQ are perpendicular to OA, then according to the description, the potential energy at OB with reference to A equal to mg into AP. Please look at the figure, then you can understand what I have written here. And at OB, the kinetic energy is 0. Okay, the kinetic energy 0 at B point. Now, my dear students, at OB, the total energy is equal to mg into AP plus 0 equal to mg AP. This is one equation. Again, at OC, the potential energy of the pendulum equal to, what will be potential energy? Equal to mg AQ. Please look at figure again. You can understand what is AQ. And at AC, at OC, the kinetic energy of the pendulum is half mv square. Okay. Now we can write half m into 2g into pq. Okay. 2g into pq. Dear students, we can write mg into pq, since v naught equal to 0 and v square equal to v naught square plus 2g. We can write mg product AP minus AQ. Please look at the figure, then you can understand AP minus AQ. At OC, the total kinetic, the total energy equal to mg AQ plus mg AP minus AQ. Finally, you get mg cross AP. Equation 2. Comparing equation 1 and 2 is clear. The total kinetic total energy at OB equal to total energy at OC. Okay. So finally we can say it is proved that in case of oscillating simple pendulum, the total energy at any point along its path remains constant. Now, my dear students, we'll discuss about freely falling body. Okay, look at the figure, then you can understand what I am going to say. The sum of the potential energy and the kinetic energy of a freely falling body at an instant is same. Okay. Now, look at dear students, let an object of mass m be raised from a point A on the surface of the earth vertically up to a point B at a height h against the force due to gravity. Please look at the figure again. Now, the total energy of the object at B is potential energy. So, the potential energy at B equal to mgh, and the kinetic energy at point B equal to 0. Okay. Now, my dear students, at point B, the total mechanical energy, potential energy plus kinetic energy, mgh plus 0, mgh, equation 1. Now, the object is allowed to fall freely from B. As the object falls to different heights, its kinetic energy continues to increases, while potential energy decreases, but total energy at any instant will remain constant. Okay, so from equation, please let after time t, the object descends through a distance x to reach c. The potential energy at c, mg h minus x. Please look at the figure, then you can understand. And kinetic energy at c, half mv square. You know this half mv square. Well, v is the velocity at c. We can write potential energy half mv square. V square means v naught square plus 2gx. Here v naught 0. That's why you can get mgx. This is equation 2. Now from this equation we can say from equation 1 and 2 we can say, or we can conclude, potential energy plus kinetic energy equal to potential energy plus kinetic energy at point C will be mgas. That is, in case of freely falling body, total mechanical energy is conserved. Okay, so the principle of conservation of mechanical energy is proved. Okay, now my dear students, homework. The first homework is, there is a body, there is a baby in a family dwelling in an apartment of top floor of a 10-story building of height 5 meters of each floor. A tennis ball of mass 100 gram released by the baby through the grill of the balcony hits the ground after few moments. You have to find out. After how much time will the tennis ball, as mentioned in the stream, hit the ground. Okay, and D, determine the total energy of ball at 7th and 4th floor of the building by using the data. Now, my dear students, is another problem. A mass of 2 kg is suspended at a point O by a 10-meter string and is set free at point A, neglecting friction and air resistance. Look at the figure. Okay. Now, from this system, you have to determine the spring constant at a point A when it is moving free. D, you have to find out, according to the stream, will be the kinetic energy of the point C different from the point B? Give the logic in favor of your opinion with necessary mathematical analysis. Dear students, third problem. The following figure shows a simple pendulum which is oscillating with a simple harmonic motion. Its maximum amplitude is Pb. The position of the bob of mass 0.2 kg at 4 positions A, B, C and D, where Pb equal to 0.6 meter, OB equal to OC equal to OD, OA equal to 1 meter. Look at the figure. Then you have to find out, you have to determine the velocity of the ball at the point A. And D, will there be any exception law of conservation of energy? You have to explain it. Dear students, that's all today, and meet you next lecture. Stay safe and secure at home. Thanks a lot.